Good morning, everyone. So here we are at part 2 of our physics lessons. We're going to look at graphing uniform motion. So uniform motion we saw the other time in our first physics lesson. It was about, the distance and the time that is being traveled by an object. So if you have a change in distance over a change in time, what we can do is we can calculate the speed that the object is traveling. So now we're going to see how we can visualize, how we can graph these distance and time graphs. So distance time graph, so first of all, let's remind ourselves, we said that speed is a change in distance over a change in time. And that uniform motion shows the relationship between two variables, distance and time. So uniform motion can be visualized using a graph. Showing the relationship between two variables. And obviously those two variables are distance and time. And so let's give an example here. So suppose we have a boat that is moving at uniform motion. And it is passing these buoys that are 5 meters apart. And so this way it's easy for us to sort of collect information. So usually we're going to start with some sort of a chart, and we're going to have time that passes, and we're going to have distance in meters. And so we're going to start with time being 0. And obviously the distance traveled by the boat is 0 meters. And then let's say that we're going to go in 2-second intervals. And so 2 seconds later, we've passed 2 of those buoys. And so we are 10 meters apart. And since it is uniform motion, you can see that as I go up by a certain amount, my distance goes up by the same amount. So it's uniform. Every 2 seconds, I move 10 meters. So then with that, what we can do is we can construct a distance time graph. And so with the distance times graph, the variable that I need to put at the bottom of the graph right here is going to be time, or we could say change in time. And that's going to be in seconds. So this is delta t. And the variable that is going to be affected by the time passing is going to be the delta d, or let's just put distance in meters, and then we'll put delta d. And if we were looking at process skills, if we were looking at the scientific method, the time, because this is the one that is sort of being manipulated, that's the one that is going to have an effect on the experiment. This would be known as the manipulated variable. As time passes, I'm expecting something to happen. And that something is I'm expecting the distance to change. So the distance, this is going to be the responding variable. Okay, so we're going to throw in some scientific method in there as well. So we're going to have manipulated variable time. The responding variable is the distance being traveled. And obviously when it comes to a graph, you should always have a title. And so for the title here, we could say this is just a distance time graph for a boat. All right, I might decide to just sort of move this a little bit. I don't know if it'll let me. There, it's a little bit more center there. Graph, and then I'm just going to move this over here, make it a little bit more center. There we go. And so then now it's time for us to put our numbers. So this is 0, and then here I have 2, 4, 6, 8, and 10 seconds. And then I'm going to put my distance. So again, I have 0. And the distance, you know, the two graduations for the graph don't have to be the same. So I can have 2, 4, 6, 8, 10 in one scale. And then here I might decide to do 10, 20, 30, 40, 50, and I'm just going to go up to 60 just so that you can see it. Okay. And so we're going to start plotting our points. And so our first point, 0, is 0. So I'm just going to put that there. It's a good idea to always circle your dot because that accounts for measurement error. And if, of course, it's a buoy, right? So 10 meters, so it might be sort of flopping around. And so the measurement might not be precise. So it's always a good idea to put a circle around your dot. And then we have 2 is 10, and 4 is 20, and 6 is 30. And here we are, okay? And then what we do with these graphs is we draw a line of best fit. So we try and make sure to go through all of, at least the circles, if not the dots, the circles. So you don't have to be super precise with it. So you can see right there, I have the line of best fit for my graph, okay? So as we can see here, one of the observations that we can make, it is a straight line. So what that means with a straight line is we have the same distance being traveled over the time intervals. And again, what do we call that when we have the same distance being traveled over time? That's uniform motion. Okay. Now, the one thing that we can see is before we get to sort of slope, and we're going to calculate slope in just a second, but I want to show you, okay, this is the graph we have for this one situation. But what if our graph looked different? So we're going to have a couple of what-if scenarios. What if the distance time graph looked like this? Oops. Trying to make this smaller. Here we go. That's the second scenario. And one more. I'm going to give you 3 different scenarios here. Okay. So we have 3 different scenarios here. So again, so always we have, you know, distance and time, meters, seconds. Same idea here. Whoops. Distance, time, and distance. time. Okay. So in this first scenario right here, I'm going to have an object that is traveling like this. And then it's doing that. Okay. Then I have an object that is traveling like this. And then it's doing that. And instead here I have an object that is traveling like this. And then it's doing that. So I want you to pay attention to those graphs and sort of have an idea of what is happening here. So this is going to call segment A and B. What is happening in segment A and B? Remember, it's distance being traveled over time. So try and see if you can think about what is happening. So the question is, what is happening during A and B? So I'm giving you a second to think about that. So what is happening during A and B? All right, so let's look at this first scenario. In this first scenario, we have an object moving at uniform motion, uniform motion, uniform motion. So I can say the same thing for all three for A. So the object in A, or at A, whatever you want to say, is moving with uniform motion. Okay, so this is the same for all three scenarios, but then what is happening at B? So in the first scenario, at B, we see that there is no distance being traveled over time. So here I had a distance changing over time, and then there is no distance being changed over time. So at B, here, the object stops. Okay, in a distance time graph, when you have a horizontal line in a graph, no slope, what it means is that the object stopped. So now let's have a look at the second scenario. So in the second scenario, the object is moving at uniform motion. And then at B, I was traveling a certain amount of distance over time. And now, look at how much more quickly my distance is changing in the shorter time interval. So at B, my object is speeding up. So the object is traveling more distance over the same time intervals, and therefore we can say that it speeds up. Okay. In the last scenario, again, what I have is the object moving at that same uniform motion that I had in the other three. And then look at that. So now one time interval goes by and not as much speed. And then another time interval goes by and not as much, speed, as much distance, as much distance, as much distance. So what we see here is the opposite that we had in the second scenario. So we have at B, the object is traveling less distance over the same time. interval, and therefore the object slows down. Okay, so that's how you can interpret distance time graphs. And then, we're going to also look at speed time graphs, and then eventually we're going to get to displacement and velocity, and that's going to be slightly different. But for these ones, you see when you look at a distance time graph, you can kind of tell what's going on. So the next thing we're going to look at is calculating slope. Now, if you remember from math, slope is your rise over your run, or you might remember it as the y-axis. We're going to take 2 points on the y-axis. We're going to call them y2 and y1, and we're going to divide it by x2 and x1, sort of a final minus initial. And when we're looking at our graph, this is our x-axis, this is our y-axis, and so what we're doing when we're doing y over x is we're doing distance y over x time. And so really what our slope is our change in distance, point y2 minus point y1, that's your change in distance. How much has it changed? And your change in x is your change in time. Oh, so wait a second. If our change in distance and change in time is our slope, change in distance over change in time is our speed. So the slope of a distance time graph will give you the object's speed, all right? So for the graph that we had above with our boat, what I'd like you to do and try is calculate the slope of the boat distance time graph. And so for that, just to remind you, what you need to do is you need to pick 2 points on the graph. In this case, it's kind of easy because it's a uniform motion graph. But remember that if you're doing it any other time, you can pick any 2 points on the graph as long as those 2 points are easily detectable. So for example, here when I'm looking at my line, I wouldn't pick this point because it's not right on there. So you don't necessarily have to pick these guys. You can pick 2 points just on the graph. So for example, I could pick this point and this point, which are right on there, or this point and that point, which are right on there, okay? And that's what I'm gonna do for this case, just because I want you to see that it works out anyways. So I'm gonna choose, my y2 is going to be 25, and my y1 is gonna be 15. Okay. So 25 meters and 15 meters. Okay. And then my x, so if I go 25, I'm looking at 5 seconds. And at 15 meters, I'm looking at 3 seconds for time. So right here, these two. So 5 and 3. So I'm going to put on there 5 and 3. 5 seconds minus 3 seconds, okay? And you can choose if you want to. You don't have to choose those points. You could choose these two, for example. But I'm just, like I said, I'm just showing you that it works either way, okay? So 25 minus 15. Do I have blue here? Yes. So I have 10 meters. And then 5 minus 3, I have 2 seconds. And so my boat is traveling at 5 meters per second, okay? Every second it passes one of those buoys that are 5 meters from each other, okay? So here's what we have for the slope of the graph. Before we move on to the next section, I want you guys to try an example on your own. Okay, so we're gonna say example 2. So again, we're gonna have an object traveling with uniform motion. And I'm going to give you a chart, time in seconds and distance in meters. And this time we're going to go 0, 1, 2, 3, 4. Let's do 5 seconds. And we have 0. Not as precise this time, or not as evident as traveling, but you can see it's still uniform motion. Okay. So for the last one, let's see. I think I might give you just 20 for the last one instead of 20.1. I think that might work better for you guys. Okay, so let's do that. And again, I would like for you to do a graph. You don't have, you could just, I'm using these because it makes it a little bit easier to graph, but you don't have to have that. So I have my change in distance and change in time, distance time graph. Get into the habit of titling your graphs, okay? And you can go ahead and plot the points on there. And then I'd like for you to find the slope, okay? And I'm gonna leave it with you. And your slope should be 4.0 meters per second. So see if you can get to that. Okay, just as an example, try it out. All right, next we get to speed time graphs, okay? So we got to look at speed time graphs. Same boat, traveling with the same motion as the one that we saw, but instead of recording the change in distance over change in time, this time we're going to be recording the speed every 2 seconds, okay? So same boat as in question or example 1. But this time, we record the speed over time, not the distance as it's passing those buoys. All right, so again, we're gonna have a little chart and we're gonna have time that goes by, and we had 0, and then 2, 4, 6, 8, 10 seconds had gone by. And this time we have our speed, which is measured in meters per second, as we saw with our slope. And so what we see here is we really see that uniform piece, right? So when we construct a speed time graph, so this time we have a speed time graph for a boat, and this time we have the change, we have the speed in meters per second, and we have the change in time in seconds. 0, 2, 4, 6, 8, 10. And let's say we go 1, 2, 3, 4, 5. There's our 5 meters per second. Now when we graph, what we see is we have that, that, that. So those are our points. I'm going to put circles around them. And so when we draw the graph, That's what we get. Okay. So what we see here, just like we did in the other one, there is no slope. There is no change in speed. If there is no change in speed, again, what do we call that? We call that uniform motion. So again, we can tell that we're dealing with uniform motion if we look at both a distance time graph. So with the distance time graph, what we want is we want that slope to be constant. We want that line to go up the same intervals for the same amount of time. If we're looking at a speed time graph, what we want to see for uniform motion is a straight line with no slope, okay? And then that'll tell us. Now, what can we use a speed time graph for? So a speed time graph can be used to calculate the total distance traveled by the object. So let's say that instead of distance and time, they just gives us speed and time, and they say, can you calculate the distance traveled by the object? And so in order for us to do that, all you have to do is look at the area under the graph. And so, okay, let's see if we can transport this little guy. Perfect. We're gonna save it. And then here we're gonna add it. Here we go. So here we have again, this is our speed time graph. And when we try and figure out the area, okay, look at this. This is the area under the graph. And so really, we're dealing with a rectangle. And so the area of a rectangle is just the length times the width, right? So what is the length of the graph? So the length is 10 seconds. So it's running those 10 seconds. Oops, don't need brackets there. And the width is the 5 meters per second. And so here, when we look at this formula, seconds and seconds cancel, and we're left with, so top and bottom, right, they cancel, and we're left with just meters. And so we see that our object has traveled 50 meters total, okay? So that's how we would use that to calculate it, okay? Now, if your speed time graph slope changes, then that's not uniform motion anymore, okay? So it doesn't matter the scenario, the area under a speed time graph will always equal the distance, but we had scenarios, right, before. Oops, wrong one. So we know what it looks like when it is uniform, but what if I have this time speed, meters per second, change in time in seconds. Okay. And all of a sudden, I don't have a graph that looks like that. What if I have a graph that changes its slope, that where the slope goes like that? So I might have, oh, wrong, I need a pen. I have something that looks like that. Or something that looks like that. So again, A and B scenarios. So what's happening at A? What is happening at B? Okay, so at A, what I have is I have uniform motion. My object is moving at the same speed over time. And then all of a sudden, the speed over time changes. What is my object doing? In this case, my object is going faster, so my speed is increasing. Whereas here, I have my object with uniform motion and then less speed over time. So here, my object is decreasing in speed. Okay. So at B, we have an increase in speed. And here at B, we have a decrease in speed. Okay. And so there you have it. Now, if you're calculating the area under the graph here, it gets a little bit more complex. So here what we have to do when we're calculating the area under the graph, because I want to figure out how my object is traveling, right? So for this section right here, I'm going to calculate this. And then I also have this section right here that I need to calculate. But to both of those, I also have to add that section right there. So I'm going to have two rectangles. So this one looks more like a square rectangle, and a triangle. And the same with this one. I have to add all the areas. So I have that. And then this time, I only have this little piece that has been traveled and that one right there. Okay, so for that, the calculation becomes a little bit more complex. And we will see what might get to that and give a couple of different scenarios. Okay, how about if you had something that looked like this, right? So if I had a speed time graph and I had uniform motion and then my object decreased in speed, and then it sort of settled itself at that, and then it decided, well, no, I want to go up in speed, and then it says, well, this is a good one, and then finally it comes to a stop at the house. Okay, so when that happens, you can see how the calculation becomes a little bit more complex, where you have to do all of these separate calculations. Whoops. You have to do all of these separate calculations, and one, this one, that one, okay? And then you have to add them all together, but really you could, if you wanted, figure out the distance that the object traveled during that time as its speed changed. All you'd have to do is calculate all those separate areas and then add them together. Okay, so that's just an example. We're never going to get to that sort of complicated. But what I'm going to do next is I'm going to give you guys, I'm going to show you a little worksheet, and I'm going to post it up, and then I will post the key next, probably by Friday. I'll post the key for the worksheet, okay? Hopefully that was good. If you have any questions, you know that we have our meet tomorrow, and we will see you then. Bye-bye.